All right, thanks, Brad, for the intro, and thanks, Tim, for helping to coordinate. There's a little bit of an agenda of what we're going to be talking about. So cutting edge, that's what Brad asked me to talk about. I certainly have been privileged to be involved on a lot of cutting edge applications and still consider myself in the midst of all of the stuff I've been able to work at, kind of you get that imposter syndrome, right? You're almost a fraud. Like, I can't possibly work on this much cool stuff. My wife actually asked me, she was like, how do you not get nervous going and talking in front of a bunch of people that are probably more brilliant than you? And I said, that's not really a problem, dear, because I have to do that every day with you. Oh, right, yeah, there you go. And that's why, the romance, why we have 4 kids, plus 1 on the way. So there's our family. I give the spiel lots of times, so we're very musical. My wife and I both started playing the piano before we were 5 years old. We love music. My house sounds like a musical. I kid you not. All of my children sing their own versions of many songs over and over again. I love coffee. If nothing else, that's a good thing to come up and ask me about for an icebreaker. Love coffee. I've got every single possible way to brew coffee. I think that's known to man other than Turkish coffee. Vacuum pot, though, the mocha pot, things like that. And then, as Brad mentioned, I've just been privileged over the last decade or so to be able to take and reduce biomimetic structures using computational design. And across the spectrum, right? Orthopedic implants is a specialty of mine. I've been able to work with large companies on the consumer goods sides to build heat transfer systems, to work on oil and gas systems as well. So it's just been a blast. So I'm going to talk about a couple applications first that are sort of here and now, and then I'm going to talk about a few future thinking applications that are a little bit in the future. I'm going to try to get through this in my 13 minutes left, so we'll see. So the first one is a company that I've been working with a friend of mine, and he came to me as somebody who's a prosthetist and somebody who works day to day with people that have partial foot amputations in particular, but other sort of problems. And one thing in particular is in the world of CAD, orthotics and prosthetics is like decades in the past. So a lot of the technologies that these guys are using are like casting people and their anatomy. So if you think about what computational design can do for something like this, it becomes immediately apparent. But a lot of the times it's just the softwares and the systems aren't necessarily made for this. So he came to me and said, hey, there's a lot of young people that have had amputations or there's some sort of deformity that just like the current stuff doesn't work for them. And what I mean is essentially it's like carbon struts, there's some thermoform pieces. The materials are either too flexible or too stiff, depending on what you're trying to do. They don't provide sufficient energy return. They're exhausting to run in. The single-piece unibody designs aren't necessarily efficient. And the biggest problem is prosthetists spend hours to create something that's bespoke for a person. And this is a similar theme, right? Med device, bespoke, patient-specific. You'll hear a lot of those things. Is an incredible way to utilize additive manufacturing and computational design. Even 3D printed products, which are starting to become a little bit more familiar, still there's a lot of things that they suffer from. Principal amongst them is just the fact that no one's really designed struts or connecting pieces that provide sufficient energy return. And again, like if you're designing and building an off-the-shelf product because you got to make hundreds or thousands or millions of them, it makes sense, right? No two people are the same. I deal with this all the time in orthopedic applications, right? Somebody's like, I need to develop a patient-specific implant. Everybody's anatomy is unique. Everybody's weight bearing is unique. Everybody's gait pattern is unique. So why are we building off-the-shelf products that are going to be a one-size-fits-all? It just doesn't work. So the idea essentially was, all right, we can do conformance. But what about like activity level? What if you could take somebody and essentially do a gait analysis and reduce the gait analysis to essentially the impacts that's happening right in their leg, and then be able to iterate and design for that? So we essentially were like, well, shoot, this is perfect application for nTop, right? So starting with geometry input through the variable inputs that we have, initial strut generation to essentially encompass the problem. Here's the design space that we're working with. Go through an FEA, do an optimization step, fill it with a lattice, analyze that, functionally grade, and then finalize and verify. So what I want to be able to, again, highlight here is, Brad sort of talked about it, is this idea that we don't just have the nTop system, we also have the way to automate it. And so automation can include being able to do lots of parts at a time. But with the nTop Automate, you can also use nTop and outer programs as a feedback loop for itself, right? So it can calculate a problem, it can send it somewhere, something can analyze, it can check to make sure whether or not it fixed the problem or whether it's still got some ways to go. I think that in your presentation or your article this morning, Brad, you called it differentiable. So differentiable systems basically means we can track the change that happens and we can measure whether or not the change was good or bad. And if we need to rerun, we rerun. If we don't, then we stop there. So this idea is that we essentially can functionally grade a structure. We can tune specifically for energy return. A lot of people tune for stress. Tuning for energy return is essentially looking at a displacement problem, which can be a little bit more challenging sometimes than just looking at stress problems. But because we can calculate vector fields from displacement, we can calculate the exact displacements on every single size simultaneously and pick the best one, which is super cool. Another thing I wanted to point out is every single gap and hole that you see is not BREP at all. That's all generated computationally. What I think is so fascinating, especially with the new nTop algorithm, is that everything is incredibly precise. So all of those gaps remain the same. All of those blocks that you see on the top and the bottom, those change with patient. And then every single hole where a bolt gets placed, that's all computationally generated. So I get a lot of people that are like, all right, I got to take my BREP geometry, I got to pull it into nTop, I could do some stuff, but I'm still relying on BREP. And I'm like, no, you're not. I'm going to design whole implant generation systems that have nothing to do with BREP at all inside of nTop. So it is possible. It just takes a little bit of a different way to view the tools than I think what a lot of engineers are used to with traditional CAD tools. The next thing I want to talk about is something that I'm super excited about, and that's I've been working with Yasmin at Uniform on the future of custom bodywear. So I think this is a predominantly male-dominated crowd. So for those of you males who may not necessarily understand the problem, ask a female in your life. But basically, here's the problem: 50% of all humans probably require some sort of support. And if you look at the metrics, 70% of consumers say that finding an online fit is difficult. Traditional sizes, again, with any product, traditional sizes don't fit bespoke bodies. Up to 100% of women have some degree of breast asymmetry. I should have put a citation. I actually found that pretty fascinating as somebody who tries to fit products to human bodies. Up to 100%, that's everybody. And even current tech online is unconvincing, right? You've seen certain AI type things that fit products onto a body, but it's just it's not really there. Something that was concepted was essentially the ability to use your iPhone, scan a body, and then using that geometry, what do we do with it? We can build computational pipeline to essentially make bespoke products on the fly. And again, I want to highlight the time reduction, which I think those of you that have used nTop are probably familiar with. Being able to take traditional sectors where designing a custom bespoke garment is going to take hours or days, and being able to insert somebody's 3D scan geometry into a pipeline and have it be done in seconds, I still get amazed at that every single time that I see it. What's even cooler is we can take measurement data across the spectrum anatomically, and we can use that to fine-tune the algorithms. So again, inside of nTop, I once was talking to Blake, he's the former CTO of nTop, and we were joking about how we use nTop as an Excel tool. We essentially just bring in point cloud data, and we use that as a way to visualize 3D graphs. I probably use nTop as a data visualizer more than I use traditional sort of spreadsheet tools anymore, which is kind of funny. And so being able to take again, anatomy from a body, being able to process that has always been something that I've been fascinated by. So being able to take a scan into nTop, being able to automatically location, feature tag, orientation. Again, these are coming in as dumb meshes with zero identifying features. Being able to automatically measure various key features, being able to segment, being able to split, being able to map. And then, what I also think is pretty fascinating about using nTop is the ability to use fields. Prior to nTop coming out, this idea about fields, sign distance fields, other types of geometry was just it wasn't in the forefront. And the sign distance fields have been used in graphics, I think, for a little bit, but now it's being used as an engineering tool. I love George's presentation talking about BREP. It's great to see that historicity behind the development of CAD tools. How many of you guys use SolidWorks? I've used SolidWorks before. How many of you guys know the SolidWorks error sound? The doo-doo. You know what I'm talking about? That haunts my dreams, man. I've used SolidWorks now for probably about 18 years. And, still use a good mix of the tools between the two because I have to, at least for now. But when I first got nTop, Brad, I think it was early alpha, 2018 sometime, even then, the ability to just build stuff and have stuff make sense, right? If, like George said, if the math works, and of course it does because it's math, then the parts work. And I was just fascinated. I couldn't break it. You know, sometimes I would do something stupid and get like a weird black-looking blobby thing, but that was my fault. That was not the software's fault. But as somebody who spent so long troubleshooting all these little tiny features, the ability to convert CAD for human use products into things that just make sense, fields that can warp and be manipulated in a map. So being able to use field-driven design to essentially every single thickness of every single shape is precisely calculated. And then also being able to create algorithm assessments of body, like for those asymmetry problems, for those people that may have some sort of deformity or issue, is an incredibly important way to utilize the tool. And being able to sort of customize profiles, adjustable, patient on the fly is pretty great. Again, dragging in geometry, output of a product that's going to fit perfectly on somebody's body in 15 seconds. I think that's pretty cool. So let's talk about some future stuff. I've been, again, privileged to be involved in lots of stuff to be able to push the limits of the tech. The additive manufacturing tech, on the panel they were talking about how 3D printing sort of surpassed computation or design tools with its complexity, and now we've got the ability to design crazy things that oftentimes are pushing the limits now what 3D printing tech can even do. So we're going to go through these. None of these are going to be super deep. You can ask me about each one of these afterwards. The first one is essentially an algorithm that was built because I was fascinated by only putting the material in a structural problem that absolutely needed to be there. In other words, I know that topology optimization says that it can do it, but I wanted to do something a little bit further. I wanted to be able to say, if my stress limit for my yield stress, something that's going to last 5 million cycles inside of a body, has to be 400 megapascals. Is it possible to essentially get it to be 400 megapascals everywhere in the structure at the same time? Most of the time, those tools, when you rerun them and you solve them again, they still have red and blue. Blue means it's not getting stressed. So what you'll notice is on the very right, by essentially tuning the algorithm to identify the direct beam pathways, we can homogenize the structure while still keeping the same design shape in the envelope. So that was a really cool problem, and it works with any structure and any loading condition, which is also cool. Being able to look at multi-physics types problem, that's a really, really important thing nowadays, right? Because very rarely are domain-specific problems singular. We don't solve for structure and then say we forget about everything else. A lot of times it's structural, there's heat, there's fluid flow, we've got some environmental concerns. So nTop provides us the ability to be able to take multi-physics informed workflows. So things like heat transfer, structural, fluid flow, all can be something that can be computed, analyzed, and weighted at the same time, which is incredibly cool. Being able to build evolutionary algorithms, I did this CDFAM last year, being able to create sort of time-dependent steps and look at responses. This particular algorithm was forced to not converge. It was forced to diverge into something different because when we look at the body, we see that there is a different biological response when bones break. Cracks start to happen. Things resorb. They don't necessarily strengthen. So I was fascinated by the idea in using nTop to do such a thing. This was an incredibly fun project to work on last year, but essentially creating overlapping shark scales and being able to apply those essentially as a field to any solid. Because what we essentially noticed was each spike is essentially compliant. So it was able to be loaded in essentially a compliant manner, but it was able to resist when the device was pulled out. So this was sort of a challenging problem that we were working on in the medical device space. So again, being able to create these sort of structures would not have been possible. My absolute favorite animal, you can ask me about him, is the mantis shrimp. The mantis shrimp structure inside of his club is unlike anything ever that has existed in nature. And when I did this back, you'll see there the visualization, the color visualization. When I worked on this 4 years ago, no one had ever modeled this structure in 3 dimensions before. It wasn't possible to do, even though you could print it, you couldn't use it. So, my mad scientist way, I was like, I just need to be able to print this. Because it is so incredibly important for things like being able to mitigate impact resistance, because that's what the mantis shrimp uses it to do. So again, prior to the advent of nTopology and computational design tools, this sort of stuff was not possible. One of my favorite things also to work on in nTop is organic foams. I'll say this, a Voronoi is not really a foam. Voronoi is certainly not trabecular bone for those of you in the orthopedic space. Being able to use nTop to create field-driven structures is really awesome. And then finally, conformal structures and textures. Brad mentioned Lattice Robot. One of the things we're trying to work on is essentially creating sort of bespoke custom structures and surface textures for people to be able to use in computational design tools. Because every single tool, every single domain-specific problem is really hard to solve, and engineers know that. So giving them the best possible structures, surface textures to be able to do that, and be able to exist in an environment to computational solve and analyze is incredibly important. So thanks so much again for the opportunity, Brad, and that's it.